Let's look at AI from an engineer's point of view. Not just another shiny tool, but as something that can actually take work off your plate. In this module, we'll see how AI can help you understand unfamiliar code, debug faster, write better tests, review changes, work with legacy systems, and automate repetitive engineering tasks. But there's one rule throughout. AI can do the heavy lifting, but engineers still need to take the important decisions. Here's something that might surprise you. Your engineering team probably doesn't spend most of its day writing code. A developer might spend 30 minutes changing a few lines, but then spend 2 hours understanding an old service, tracing a bug, reviewing a pull request, searching documentation, or figuring out why a test is failing. And that's the opportunity we're going to explore in this module. AI doesn't just help engineers type faster, it can help them understand faster. Imagine a developer joining a project and asking, where does this request enter the system? Which service handles it? Where is the data stored? And which tests cover this behavior? Instead of spending hours hunting through the repository, AI can help build that initial map. So when you look for AI opportunities in engineering, don't start with coding. Start with understanding, debugging, reviewing, and context switching. That's where a surprising amount of engineering time actually disappears. There's a bigger change happening here than simply getting better code completion. Think about how we started. Autocomplete meant, finish this line for me. Then came coding copilots, help me build this function. Now we're seeing coding agents move towards something much larger. Investigate this issue, understand the repository, make the required changes, run tests, and prepare the work for review. That's a very different unit of delegation. We're moving from a line to a function to an engineering task. But here's the important part. The engineer isn't disappearing from that loop. The engineer increasingly defines the objective, constraints, and acceptance criteria, then inspects what the AI produces. So the skill isn't simply learning how to prompt a coding tool, it's learning how to delegate engineering work intelligently. And that's going to be a major theme throughout this module. AI is not equally good at every engineering task. So instead of asking, what can AI do, ask, which parts of engineering work are naturally suited to AI? For example, AI is very useful for exploring an unfamiliar codebase. It can generate first drafts of tests or boilerplate. It can transform repetitive code during a migration. It can analyze patterns across files. It can suggest edge cases. And it can turn code changes into documentation or release notes. Here's a practical trick. Take a repetitive engineering task your team performs every week. Don't automate it immediately. First, ask an AI tool to perform the task on 5 real examples. Then, review the results. You'll quickly discover whether the task is predictable enough for AI assistance. The goal isn't maximum automation. It's finding the right level of delegation. Here's where we need to slow down. AI can write code remarkably quickly. That does not mean the code is correct. It might make an assumption about your architecture that isn't true. It might miss an edge case. It might introduce a security weakness. Or worse, it might generate tests that pass while testing the wrong behavior. That's why your engineering workflow should look like this. AI output, engineer review, tests, security check. Think of AI-generated code as a very fast first draft. Would you merge a junior developer's unreviewed code directly into production? Probably not. Treat AI-generated code with the same discipline. A useful habit is to ask the AI, explain the assumptions you made, then inspect the actual code and run the tests. Remember, generated code is an output. Verified code is an engineering result. This is one of the most important changes in the module. The traditional workflow was often implement, test, ship. But AI introduces another layer. Now we can think in terms of specify, plan, delegate, implement, inspect, test, ship. And notice where the human becomes particularly important. The human specifies the goal. AI can help plan. The human delegates, AI can implement. Then the engineer inspects, tests, and decides whether the work is good enough to ship. That changes the engineer's job. You're no longer necessarily typing every instruction yourself. You're managing an engineering loop. Try this tomorrow. Instead of saying, build this feature, write a short specification first. Define the goal, constraints, and expected behavior. Then ask AI to propose a plan before it writes code. You'll often catch misunderstandings before any code is changed. That's a much safer way to use coding AI. Here's a mistake I see all the time. Someone opens an AI coding tool and immediately says, build this feature. That's backwards. Before asking AI to code, give it 5 things. What needs to change? Why does it matter? What must not change? How will we know it works? And finally, give it examples of the behavior you expect. For example, we need to change password reset behavior. Existing authentication must remain unchanged. Expired links should return a clear error. The new behavior must be covered by automated tests. That's dramatically better than fix password reset. Here's your practical rule. Write the acceptance criteria before you write the AI prompt. Your AI tool can generate code. It can't rescue a badly defined engineering problem. Would you hire a developer and ask them to modify a system they've never seen without first explaining the architecture? Of course not. So don't expect AI to work that way either. Before changing anything, ask AI to map the repository. Where are the entry points? What are the main services? How do those services communicate? Where are the dependencies? Where does data flow? And importantly, don't change anything yet. This is a powerful workflow. First, ask for understanding. Then, review the map. Correct anything the AI misunderstood. Only then, ask it to propose a change. This gives you a second benefit. You may discover that your own mental model of the system is outdated. So, repository mapping isn't just useful for AI, it's useful for humans onboarding into the system too. Imagine you've inherited a service nobody has touched for 2 years. There are thousands of lines of code. No one remembers exactly why some of it exists. What do? You could spend hours reading files from top to bottom. Or you could start with an AI-assisted map. Ask, where does the request enter? Where does the business logic happen? Where does data come from? Which components call each other? And which areas look fragile or poorly tested? Now you have a starting point. But here's the important part. Don't immediately trust the map. Use it as a hypothesis. Verify the important paths yourself. Then go deeper. This is one of the best uses of AI in engineering because it reduces the cost of getting context. And context is often what slows experienced engineers down when they enter unfamiliar systems. Here's a surprisingly useful rule. Don't start debugging by asking AI to fix the bug. Give it the investigation first. Imagine your users are reporting intermittent payment failures. Don't say, fix payment failures. Instead, give AI the symptoms, relevant logs, recent changes, and expected behavior. Then ask it to reproduce, trace, hypothesize, inspect, identify the likely root cause. Only after that should you discuss a fix. Why? Because debugging isn't simply a search and replace exercise, it's a reasoning problem. If you ask AI for the fix too early, it may jump straight to a plausible solution without understanding the actual cause. You want the AI to help you investigate, not simply guess. A useful prompt is, don't modify the code yet. First, give me your 3 strongest hypotheses and the evidence that would confirm or reject each. That changes the quality of the conversation immediately. Now let's take debugging one step further. Never accept the first explanation just because it sounds convincing. Give AI the symptom, provide the logs, ask for multiple possible causes. Then ask, what evidence would prove each hypothesis? Now test those hypotheses. Maybe the AI thinks the database is timing out. Fine, check the database metrics. Maybe it thinks a recent deployment caused the problem. Check the deployment timeline. Maybe there's a concurrency issue. Look for evidence. Only after you have enough confidence should you implement the smallest fix. And then add a regression test. This creates a disciplined loop. Evidence, hypothesis, test, fix, regression test. That is much stronger than problem, AI guess, copy fix. Your goal isn't to make AI sound confident. Your goal is to make AI show its reasoning against evidence. Here's a simple question that can dramatically improve AI-assisted engineering. What could break? Developers naturally think about the happy path. If the input is valid, the database is available, and the user behaves normally, does the feature work? Great. But production rarely behaves that politely. What happens with an empty input? A timeout? An invalid value? A duplicate request? A failed dependency? A user who clicks twice? This is where AI can become useful as an adversarial thinking partner. After generating a feature, ask, "Give me the 10 most likely ways this implementation could fail." Then ask it to group those failures into input problems, dependency failures, concurrency issues, security risks, and unexpected user behavior. Now, you're not just asking AI to create code, you're asking it to challenge the code. That's a much more valuable use of AI. Here's a trap engineers know well. You see 80% test coverage and feel pretty good. But coverage doesn't necessarily mean behavior is well tested. What happens if the database suddenly becomes unavailable? What if the same request arrives twice? What if the user retries immediately? What if a timeout happens halfway through the operation? What if two operations happen at exactly the same time? Those scenarios may not be represented by your line coverage number. So here's a practical AI exercise. Give the AI your existing implementation and tests. Ask, what important behaviors are currently untested? Then ask it to classify the gaps: happy path, edge case, failure case, boundary condition, concurrency, security. From there, choose the tests that actually matter. The goal isn't to produce thousands of tests, it's to produce the right tests. Because good testing is about confidence, not volume. Here's another practical use for AI. Make it your second reviewer. Imagine you open a pull request. Before the human reviewer even looks at it, AI can inspect the change for possible issues. Logic errors, missing tests, security concerns, performance problems, unexpected side effects. It can surface questions such as, could this create a race condition? Why isn't this error handled? Is this input validated? But notice where AI belongs in this workflow. It's not the final approval. The engineer still reviews the change, tests still run, and the human decides whether the code should merge. That's the right relationship. AI can increase the number of things we notice. Humans remain responsible for deciding what matters. So don't think AI replaces code review. Think AI makes code review more informed. Here's a project that scares almost every engineering team, a 2,000-line service that nobody wants to touch. The temptation is to say, let's rewrite it. Don't. Start by mapping dependencies. Then identify safe boundaries. Maybe the service actually contains 4 separate responsibilities. Extract one, refactor it, run the existing tests, compare the behavior, then move to the next component. AI can be very useful here because it can help identify repeated patterns, suggest smaller refactoring steps, and generate supporting tests. But the important word is small. Don't give an AI agent a giant instruction to rewrite the entire service and hope for the best. Give it one well-defined transformation at a time. That's the principle. Small, verified changes beat one giant rewrite. Legacy code isn't difficult only because it's old. It's difficult because the knowledge around it has disappeared. The original developers may have left. Documentation may be incomplete. Business assumptions may be buried inside code. Nobody remembers why certain decisions were made. AI can help make that system navigable. Start by asking it to explain the major components, then document the architecture, then identify critical paths, then create tests around existing behavior. Only after that should modernization begin. Think of the sequence: understand, document, test, modernize, verify. And there's a valuable side effect. You're turning invisible knowledge trapped inside a code base into knowledge that the whole team can access. That's why I see AI as particularly useful for legacy systems. It isn't just helping you write new code, it's helping you recover lost engineering context. Large migrations become frightening when you treat them as one enormous task. Let's say you're moving from an old API to a new API across 1,000 files. Don't touch all 1,000. Start with inventory. Find every call site. Understand the different patterns. Then take 10 files and perform a pilot migration. Validate it. Now you've learned something. You can encode the transformation rules. Then move to 100 files. Validate again. Then 500. Then 1,000. This is where AI can be extremely useful. Once you understand the transformation pattern, AI can perform repetitive changes across many files much faster than a human doing them manually. But the sequence matters: inventory, pilot, pattern, scale, monitor. Don't scale an unverified transformation. Prove the pattern first. Let's talk about something engineering teams often postpone: documentation. AI makes documentation much easier to produce, but there's an important distinction. Good documentation isn't simply, "What does this function do?" It also needs to explain, "Why does this system work this way?" AI can combine information from the code, architecture, change history, and operational knowledge to help create API documentation, README files, architecture explanations, release notes, runbooks, change summaries. But don't ask AI to document a system it doesn't understand. Give it the repository context, give it the architecture, give it the relevant business context. Then ask it to explain the system for a specific audience. And finally, have an engineer review it. Good documentation isn't decoration. It's part of keeping an engineering system maintainable. Now imagine this message appearing at 2 a.m. API latency has doubled. What happens next? Someone starts checking logs. Someone checks the latest deployment. Someone looks at metrics. Someone asks whether another service is failing. The challenge isn't necessarily a lack of data. It's too much data arriving at once. AI can help organize that context. Feed it the relevant timeline: recent deployments, error logs, metrics, configuration changes, known incidents, dependencies. Then ask, what changed before the latency increase? What signals correlate with the incident? What are the 3 strongest hypotheses? The AI doesn't magically solve the incident. It helps the engineer structure the investigation faster. And when production is burning, reducing the time spent searching for context can be incredibly valuable. AI shouldn't sit outside your engineering process. It should work inside the process you already trust. Think about the pipeline: commit, build, test, security check, review, deploy, monitor. AI can assist at several points. It can generate tests, explain why a build failed, summarize a change, identify possible risks, draft release notes, help investigate a failed deployment. But there's a line we shouldn't cross. AI should strengthen the pipeline, not bypass it. Don't let an AI-generated change skip testing because the agent said it works. Don't remove security checks because the code looks clean. And don't eliminate review because AI generated the change. The pipeline exists to create confidence. AI should make that pipeline more efficient while preserving its safeguards. This is one of the most important warnings in the entire presentation. AI can help identify hard-coded secrets, unsafe dependencies, injection risks, missing validation, weak authentication. But AI security review is only one layer. Think about your security stack: AI scanning, static analysis, dependency scanning, automated tests, human security review. Each layer catches different things. Here's a simple rule for your team. If AI generates the code, don't reduce your security standards. In fact, you may want to increase your scrutiny initially because AI can introduce subtle vulnerabilities at scale. And remember, a model saying this code looks secure is not a security control. Use established security tooling and engineering review. AI can be the first line of detection. It should never be the last line of defense. Technical debt doesn't usually arrive with an alarm. It quietly accumulates. One workaround, one duplicated function, one outdated dependency, one fragile service, one missing test. Then, 6 months later, developers are spending hours working around problems instead of building new capabilities. AI can help turn that invisible debt into a map. For each issue, ask 5 questions. What is the problem? Why does it matter? What happens if we ignore it? How difficult is it to fix? And what value do we get if we fix it? Now you can prioritize. Don't fix technical debt simply because it looks ugly. Fix the debt that creates the biggest operational, reliability, or engineering cost. AI helps you create the map. Engineering leadership decides where to invest. Developers naturally ask, can AI write this? Engineering leaders should be asking a different question. Where should we use AI? Where is engineering time disappearing? Which tasks are repetitive? Where are incidents expensive? Which teams are spending too much time on maintenance? Where is technical debt growing? And where can AI increase capacity without increasing unacceptable risk? This changes the conversation completely. An engineering manager doesn't need every developer using AI in the same way. They need to understand where AI creates measurable leverage. Maybe one team gets value from test generation, another from incident investigation, another from legacy code understanding, another from documentation. The goal isn't maximum AI usage. The goal is maximum useful engineering leverage. Here's another misconception worth clearing up. AI isn't replacing your engineering stack. Your repository still matters. Your test suite still matters. Your CI/CD pipeline still matters. Your observability tools still matter. Your security controls still matter. In fact, AI works better when it can operate with the context those systems provide. Think of AI as another participant in the engineering environment. It can understand the repository, work with issues, use the test suite, interpret build failures, help investigate observability signals. But the surrounding engineering infrastructure remains essential. This gives us a useful mental model. AI doesn't replace engineering discipline. It makes that discipline more accessible and potentially more powerful. So don't build an AI island. Connect AI to the workflows your engineers already use. Here's how I would approach an AI initiative if I were working with your engineering team tomorrow. I would not say, let's introduce AI across engineering. I'd choose one workflow, maybe bug triage, maybe test generation, maybe pull request review, maybe documentation, maybe incident investigation. Then establish the baseline. How long does it take today? How much does it cost? What's the quality like? Then define the target. For example, reduce PR preparation from 30 minutes to 10 minutes without increasing escaped defects. Now you have something you can test. This is much better than saying, we want to increase AI adoption. Adoption isn't the outcome. Improved engineering performance is the outcome. You don't need a 6-month transformation program to find out whether AI can help. Run a 2-week experiment. During week 1, choose the workflow, collect your baseline metrics, select 10 to 20 real examples, and define success criteria. During week 2, run the AI-assisted workflow, review every result, measure the improvement, record failures, and then make a decision: stop, improve, or scale. Let's use the example from this slide. Suppose PR review preparation currently takes 30 minutes. Your target is 10. But there's another condition. Escape defects must not increase. That's important, because reducing time while damaging quality isn't a successful AI implementation. This is how you make AI experimentation scientific rather than emotional. Don't ask, did the team like the AI? Ask, did the process improve? Here's where many AI pilots go wrong. The team gets excited because developers generated more code. But more code isn't necessarily more value. Instead, measure what engineering leaders actually care about. Speed. Did the task become faster? Quality. Did defects decrease? Coverage. Did important behavior become better tested? Reliability. Did incidence or recovery time improve? Developer experience. Do engineers actually find the workflow useful? And finally, cost. What are we spending on the AI and supporting infrastructure? Imagine AI increases code output by 30%, but production defects increase by 20%. Would you call that success? Probably not. The real question is, did we improve the engineering outcome? That's the metric that matters. AI excitement is temporary. Engineering impact is measurable. This is probably the biggest takeaway from the entire module. The engineer's job is moving upward. Some traditional work involved manually writing code, fixing syntax errors, searching documentation, and repeating transformations. AI can increasingly help with those activities. So where does the human create more value? In defining intent, designing systems, making architectural decisions, reviewing AI output, managing risk, understanding business requirements, building feedback loops, and deciding what should actually ship. That's not less engineering, it's a different kind of engineering. AI reduces the value of typing every line. It increases the value of knowing what should be built, why it should be built, and how to prove that it works. So don't compete with AI at typing. Learn to become better at engineering judgment. That's where your leverage grows. And that brings us to the final step before the capstone. If you followed this journey from the beginning, you've moved a long way. You've gone from understanding what AI is to understanding how it works. You've learned to prompt it, build workflows, use tools, work with agents, connect AI to your data, evaluate its output, apply it to knowledge work, business, and engineering. Now comes the most important part. Build something real. Don't build a toy just because it's easy. Find a problem that matters to you, something repetitive, something frustrating, something expensive, something that takes too much time. Then ask, can AI make this meaningfully better? That's what Module 15 is about. So subscribe to the Genius Circuit, continue the journey, and visit www.thegeniuscircuit.com for more practical AI learning. The goal was never to learn AI. The goal was to learn what you can build with it. I'll see you in the capstone.